This is the fourth lesson of our last unit, Unit 8, on probability. Specifically, this note will cover comparing experimental and theoretical probability. So just as a quick recap, theoretical probability is the mathematical probability that is calculated without actually doing the activity, opposed to experimental probability, which is the probability observed, when performing an experiment. Okay, so although the formulas are quite similar, they do differ slightly. So for theoretical probability, the general formula is the probability of event equals the number of successful outcomes over the total number of possibilities. Okay, experimental probability, on the other hand, again, your probability of your event is the number of successful trials. So remember, we defined trials in our first note. Divided by the total number of trials. So very similar. Again, the major difference is that with experimental, you're actually doing the experiment. With theoretical, it's more of just a mathematical probability of possible outcomes. Okay, so the theoretical probability of rolling a 2 with a single die is 1 in 6. However, if you try it, do you suppose you will roll exactly 1, 2 in every 6 trials? So if you have a dice around, or a die around, try this out if you're not sure, right? So even though the theoretical probability of rolling that 2 is 1 in 6, if you try it, it's probably not going to work. Like if you roll a die 6 times, you're probably going to get 2 more than once, or maybe not at all. So no, we don't suppose that it will actually work. And the reason for that is because reality and theory are not technically the same. They're not necessarily the same. So again, hopefully you tried that out, and you could see that. Suppose you toss 10 coins at once repeatedly. How many heads should occur in each toss? So again, we figured out the probability, and this was in like maybe our first unit. There's two options, right? There's heads or there's tails. So the probability of getting heads is typically 1 in 2, right? It's a 50-50 shot on getting heads or tails, which is why we flip a coin a lot of times in sports, or if we're betting, something like that, and choosing one of those sides, because the chances of getting heads or tails are equal. So in order to figure out how this works, if we are tossing it 10 times, all we have to do is multiply that value by 10. Okay, and again, remember, when you're multiplying fractions, you can picture a whole number over 1. So 1 times 10, I'll do it over here. 1 times 10 is 10, and 2 times 1 is 2. 10 divided by 2 is 5. Okay, so if you are tossing 10 coins, obviously half of that would be 5. So you would theoretically think that 5 heads should occur. Explain why you will not necessarily see 5 heads every time. So the reason for this is because probabilities are like averages. Probabilities are like averages. Okay, so that means it's not always going to work, right? If you just do an experiment one time, it's actually more likely that you won't get the exact probability. But if you do the experiment enough times, the experimental probability will actually get closer to the theoretical probability. Okay, so if you kept repeating that over and over and over again, you likely, and I'm sure you did this in elementary school where you flipped a coin or rolled some dice or something like that, and you did it like 100 times, and eventually your outcomes were pretty close to what the theoretical probability told you should end up with. Okay, so moving on to our next example. A modified dartboard has equally spaced sectors containing the numbers 1 through 20. What is the theoretical probability of hitting the numbers 18, 19, or 20? So the probability of hitting 18, 19, or 20. Okay, if you're not familiar with darts, what that's saying is that there's 20 different things like this. They're equal, so this isn't a great example, but each of these slots would be equal. Okay, and the numbers only occur once, 1 through 20. Okay, so the probability of hitting 18 would be 1, right? You'd have one slot of 18, one slot of 19, and one of 20. So that's 3 in total out of a possible 20, right? There's 20 different areas on your dartboard. So, again, if you do 3 divided by 20 times 100, that will give you around 15%. So there's a 15% chance that you would hit 18, 19, or 20. In 75 of the first 80 throws, a dart player hits the numbers 18, 19, or 20. Find the experimental probability of hitting 18, 19, or 20. So he threw 75 times and he hit all 3 of those within those 75. So that means that he was successful in 75 out of the 80 throws. 75 divided by 80, again, we can reduce that. That's the same as 15 over 16. Divide those out, you will get a 94% chance. Okay, so the second is experimental, the first is theoretical. So what happened here, right? We know that the 15% to 94% is a huge, huge difference, right? So theoretically, he should have had a 3 in 20 chance of hitting 18, 19, or 20. But in reality, he actually hit 18, 19, or 20 94% of the time. So part C says, would you expect the experimental probability to approach the theoretical probability if the number of throws increased? So you need to have a little bit of background in darts kind of to understand this, and I really don't, but assuming that he wanted to hit 18, 19, or 20, right? He was aiming at them. That means that 1 through 17 were less likely to be hit, right? Because he actually wasn't aiming at them. So we wouldn't expect that the experimental probability would get closer to the theoretical probability, again, because he's aiming for these specific areas on the dartboard. So we're going to say no because each outcome is not equally likely. And that is because the player is aiming at 18, 19, and 20. Okay, he's not like blindfolded throwing the dart and just seeing where it goes. If he was blindfolded and he wasn't necessarily aiming, or maybe we should talk about not like an actual dart player. If you or I were just standing there and closed our eyes and aimed at the dartboard generally and threw it, that would kind of account for this theoretical probability, right? For us, it might be a 15% chance that we hit 18, 19, or 20. But if we're actually aiming at those, there's going to be a higher chance, assuming that we're somewhat accurate in our throws. Okay. So last example here. So suppose a couple would like to have 3 children. Determine the theoretical probability of having 2 girls and 1 boy. Okay, so we're going to set up our tree diagram here. So we have 3 kids. So child 1, 2, and 3. And I realize that this is a little outdated in terms of gender, but let's just assume there's only 2 options for this example. Okay, we're talking about like the sex that you are born as. So the first child could be born as either a girl or a boy, right? The second child, if the first was a girl, the second one could be either a girl or a boy. And if the first was a boy, the second could also be a girl or a boy. So I'm hoping you're kind of getting the hang of these diagrams. So if we had 2 girls, the last one could be either a girl or a boy. If we had a girl and a boy, the last child could be a girl or a boy. If we had a boy and then a girl, we could also have a girl or a boy as our last one. And if we had a boy and a boy and a girl and a boy. Okay, so lots of options there, right? So let's just write them out because this tree diagram is a little bit messy. So again, you're just reading your tree diagram. So you have a couple different possible outcomes. Possible outcomes. So we could have girl, girl, girl. We could have girl, girl, boy. Girl, boy, girl. Girl, boy, boy. So that's the top half of our diagram. That's if we have the girl as the first child. Or we could have, whoops, boy, girl, girl. Oh my gosh, what is my numbering system here? Try that again. 5. We could have boy, girl, boy. We could have boy, boy, girl. Or we could have boy, boy, boy. Okay, so those are all of the possible outcomes. So this question specifically is asking us, what is the theoretical probability of having 2 girls and a boy? So let's go through and find any situation where there's 2 girls. It doesn't matter what order they're born, but 2, whoops, I want to change my color. 2 girls and a boy. 2 girls and a boy. 2 girls and a boy. So we have 3 situations where we're correct, or we're getting this situation. So probability of 2 girls, 1 boy is equal to 3, right? 3 is the amount that we're successful out of a total of 8. Again, divide those on your calculator. that's a 38% chance of getting 2 girls and a boy. Okay. Part B says, explain how your answer in Part A can help you determine the theoretical probability of having 2 boys and 1 girl. So it's asking you for the probability of now 2 boys, 1 girl. Okay. Because it's a 2-to-1 ratio, the probability is going to be the exact same, theoretically. Okay. So that's why when you have that 38%, you can assume that it's also going to be 38% that is getting of these people getting 2 boys and 1 girl. So we would just say the probability is the same as 2 girls, 1 boy, which is 38%. Okay, and again, that's theoretically, right? It's not like these kids are being born as we do this experiment. This is just us trying to figure out the likelihood that this will happen. Okay, determine the theoretical probability of having at least 1 girl. So again, we're going to go back up to our options here and see in how many situations are we going to have at least 1 girl. So I'm going to use a different color, so orange. So what will I do? I'll put an X this time. So 1 girl, at least 1 girl, at least 1 girl, at least 1 girl, girls, girl, girl. Okay, so we can see that there's only one situation where this isn't going to be possible, right? So the probability of 1 plus girl is 7 out of 8, right? In 7 out of 8 of those situations, you are getting at least 1 girl, which is an 88% chance that you theoretically would have at least 1 girl. So keep in mind that a lot of people have children, and this isn't necessarily the case, right? Some people have more than 3 children, and they are this kind of 1 in 8 chance of getting just all boys or all girls for that matter. Okay, almost done here. It says determine the theoretical probability of having 3 girls. So again, I go up to my options here. I'm just going to underline. There's only 1 chance, right? There's only 1 out of 8 of these possibilities where we have 3 girls. So the probability of 3 girls is 1 in 8, okay, which is only a 13% chance. So there's a 13% chance that these people would have just 3 girls. Okay, last question. Suppose the couple hopes to have a boy first and a girl second. What is the probability of that happening? So a boy first and a girl second. So back up to our options here. Get a different color altogether. Was it boy first? Yeah, boy first, girl second. So boy first, girl second, boy first, girl second. Okay, so those are the only 2 options where that BG occurs. So the probability of boy, girl is 2 in 8. Okay, which again, we could divide those by 2. That's 1 in 4, which we should know is 25% chance. Okay, so again, you need to understand the difference here between theoretical, right, in theory, versus actually when these experiments are happening. It's not always going to add up to the same number. So this is the end of our 4th note of probability.